Hey guys, welcome back. So let's start talking about dissolution, forces, and properties. Okay, that's the next thing that we're going to be talking about. So, what are we talking about in terms of dissolution, forces, and properties? Well, let's talk about that. So, the first thing is going to be dissolution in water. And what do we mean by dissolution in water? Well, when we're talking about dissolution in water, we want to know what happens when we put stuff into water. So, how many particles does that thing break up into? What forces exist when that happens? What properties would expect based on those forces? What is the energy associated with that process? How fast does it happen? What are the kinetics for that? We'll talk about the energies and kinetics later this semester. Do all the salts dissolve, or does some of it stay in, not dissolved in the solution? Is some of it still solid? Are there other things in our system that the material can react with? And what is the concentration of the solution that we have now that we've done this? So let's consider first the number of particles that come into the solution when we add them to water. And of course, if I want to do that, I need to know, is this thing ionic or not ionic? Okay. If it's ionic, it completely dissolves. If it's soluble, and we'll talk about solubility and what that means. You may have heard of it already, but we'll talk about those rules and what that means a little later on. The number of particles that it becomes once it goes into the solution is related to not only the initial concentration, but also to the number of ions present in the species. So when I talk about something like NaOH, when that goes into solution, I get an Na plus and an OH minus. And so the Van Hoff factor, is 2. Van Hoff factor, again, being I, is the number of particles that species becomes when dissolved. And of course, here we're talking about being dissolved in water, but it's not necessarily in water. It can be in any given solution that we want to talk about. So NaOH becomes an Na plus an OH minus, and the I for that is 2. When we talk about Mg3PO4 2, that comes apart, gives me 3Mg2 plus 2PO4 3 minus, and the I for that is 5, because I get 5 particles out of it. Now, glucose is not ionic. It does not dissociate. And so the I for glucose is 1 because it does not dissociate when it comes into solution. Now, HF is ionic. The thing is, though, when HF goes into solution, that HF is a weak acid. Okay, we'll talk about why later. So that's true. So I may get 2 I's out of this. The I is still 2 for this, but the concentration that we put in is not equal to what we put into that solution. And so we're going to have to do some math for that later. That's what we'll be talking about when we talk about acid-base ionization in one of the later lectures. Okay, and I think that's lecture 3. So that's what we're talking about there. So I is the Van Hoff factor. It tells me how many pieces of this thing I get when I dissolve it in solution. And that's entirely based on whether it's ionic or not. And if it's ionic, even if it is, if it's not soluble, okay, then that's going to change that. And we'll talk about solubility a little later on too. So there's that. So that's awesome. But we also have to talk about what happens once that dissolves. So let's think about this HF. So when we get HF coming apart, sorry, you couldn't see that. When I get HF coming apart, I get an H plus and an F minus, right? And I might be interested to know what happens when H plus is surrounded by an OH with 2 lone pairs on it, because that's my water molecule. So what kind of interactions can I get between those 2 things? And that's the next thing we want to talk about. And those are the forces. There are 4 types of forces that we need to deal with. And I'm going to go from strongest to weakest. The strongest is hydrogen bonding. We then have ion dipole dipole, and then van der Waals. Now, hydrogen bonding only exists between hydrogen and either an oxygen, a fluorine, or a nitrogen. That's the only time I can get that. An ion dipole must have an ion present. So since the H plus is an ion, we could have an ion dipole here. The ion comes from the H plus. The dipole would have to come from the water. Now, does water have a dipole? Absolutely it does. Because those electrons are pulled towards the lone pairs. And of course, the bonds here are polar, so the electrons are pulled that direction anyway. So all of my electron density is up at the top. So I have a partial negative charge, and that's supposed to be a delta, and a partial positive charge. And so that's a dipole. That's a permanent dipole moment. So water has a dipole, so I can get an ion-dipole interaction for this particular species. Okay, can I have a dipole-dipole? Well, I can for the waters, but not for the HF, right? Now, HF, when it's still together, does have a dipole, and that's actually like that as well. So there is a dipole-dipole interaction for this because it is a weak acid. So that is correct. So we have that as well because it's not a strong acid. And van der Waals, what van der Waals is at any given second, all of the electrons in a particular molecule may be completely on one side or the other. That happens from time to time. And when it does happen, that means that the electrons are all on this side of this molecule, on the right side of this molecule, and the left side of the one next to it. Then they can be attracted to each other. Okay, that is something that can happen. All right, and that happens all the time. It's very transient. Everything has van der Waals forces. Everything. I don't care what it is. So that is always going to be present. The question is, are any of these other things going to be present? And of course, what we're looking at right here with this H and this F, we have all of those. Now, depending on what forces we have, that will determine what kinds of properties we would expect to see. And so let's talk about those properties. What are we talking about in terms of properties? Well, things that we could be talking about is how much energy it takes to vaporize this. So if I have this in solution, how much energy would it take for this thing to go to the gas phase? And since HF has additional intermolecular interactions compared to water, there's the hydrogen bonding that exists and the ion dipole that exists and the dipole-dipole that exists that are different than they would be in just water, we would expect that to be slightly higher than it would be for just water. Okay, so additional forces mean additional energy that's required to make that thing turn into a gas. We would have lower vapor pressure because we have HF in this thing now. So we don't just have H2O at the surface. And so if we don't just have H2O at the surface, then it's harder to get those things to come out. H2O is inhibited from coming out by the presence of the HF. We also have a higher surface tension because more individual hydrogen bonding, more ion dipole interactions, more dipole-dipole interactions means that at that surface, we're going to be pulling net downwards. And so that's a higher surface tension. All of these things are the properties that we can be talking about. So freezing point, boiling point, vapor pressure, vaporization energy, resistance flow, greater capillary action, all of those things will be impacted by the forces that we see. Whether we talk about those or not depends on what we're talking about, okay? But that is something that may become part of the discussion that we need to have. So we need to be able to think about what those forces are and how that might impact whatever it is we're trying to talk about, okay? So questions on dissolution in water, the forces that then come from that, or the properties that then come from that. And I hope not, but you know that if there are, please let me know. I'm going to stop again, give us a break one more time, and then we'll move into the next part of this. And I can't remember what's next. What is after this? Gases, acid base, and precipitation. Okay. See you soon.